For this video, I'd like to talk about the quadratic formula and how we actually use it. Though, before we talk about actually using the quadratic formula, I'd like to at least introduce why we use it and when we'd use it. So, this formula essentially comes out of a very general quadratic equation. So if we write it as y is equal to a times x squared plus bx plus c, this is essentially our most general quadratic equation where a, b, and c can be any numbers we choose. For instance, we could have 3x squared minus 4x plus 7, where a is 3, b is minus 4, and c is 7. Though the truth is we could choose any values we want for a, b, and c. And that's essentially why we say this equation here is the most general quadratic equation, since it essentially covers every possible quadratic equation that we could have. So you might be wondering, why do we use this formula, or when do we use it? So let me draw a quick coordinate plane, and we'll look at essentially some random quadratic equation and what its graph looks like. So remember, these things all form the shape of a parabola. So it might look something, let's say, like this, where these quadratics always have a vertex, its lowest or its highest point, and what you'll see is that most of them will cross the x-axis here. So we'd have these points here and here. These are called the intercepts, the x-intercepts to be specific. And notice that the y value for every point along this line is the same. Namely, these points are all along the y value of 0. So what we can do with our general quadratic equation is essentially set it equal to 0 if we want to know what these points are. And these points are what we call the zeros of our quadratic equation. And once we set this general equation equal to 0, we essentially are able to solve it and turn it into this quadratic formula here. And the way that we solve this, I might cover in a later video, but it's essentially using a process called completing the square. And like I said, we're not going to talk about it in this video. I'm not going to show you how we get the quadratic formula, but I mainly just want to show how we use it. So let's now look at a specific example now that we know that this formula is essentially just finding the x-intercepts of our parabola. So with that in mind, so we can look at the example. Y is equal to x squared plus 2x minus 3. And we're comparing it to our general quadratic equation, which we set equal to 0. So we need to figure out what our a, b, and c values are. And a is just the number multiplied by x squared. And if you don't see a number there, you can assume that it's 1. So in this case, a is equal to 1. And b, the number multiplied by x, would just be positive 2. And then lastly, we have c, which is essentially the constant at the end of our quadratic. So in this case, it's equal to minus 3. And then let me just quickly rewrite the quadratic formula since we're going to use it. And with this quadratic formula, we essentially now just need to plug in anywhere we see b, a, or c. We need to exchange it for a equals 1, b equals 2, and c is equal to minus 3. So let's do that. So we say that x is equal to minus b, but b is that value of 2. And then we have plus or minus the square root of b squared. So we again have that 2, but we're squaring it. And from there, we have minus 4 times a times c, where a is that 1, and c is that minus 3. And then after this, we're going to divide everything by twice a, and again, a is that value 1. So once you've essentially substituted everything into the equation, at this point, it's just a matter of simplifying this. So let me make a little bit more space. So we get the opposite of 2, so minus 2, plus or minus. We have 2 squared, which is 4. Then we have minus 4 times 1 times negative 3. And minus 4 times minus 3 would be a positive 12. And then times 1 would still keep it at 12. So the net result of minus 4 times 1 times minus 3 would be a positive 12. Those two negatives canceled each other out. And then all this divided by 2 times 1, which is 2. And we can simplify underneath the square root sign. That's just 16. And the square root of 16 has a nice clean value. It's a whole number, namely it's the value 4. And once you get it down to this step, we essentially have two solutions. And I should mention that essentially because we're dealing with a quadratic, or because the highest power of x in our equation is 2, we should expect two solutions. And that's what's known as the fundamental theorem of algebra. So whatever the highest power of x is in your equation, that's generally how many solutions you have. So if you have an equation with x to the 4th in it, then you should expect 4 solutions. So for us, we expect 2 solutions, and we ended up getting that. So the plus is one of our solutions. So namely, if we do minus 2 plus 4 divided by 2, so that's one solution, whatever that simplifies to. And then we have minus 2 minus 4, all divided by 2. And so we can just simplify these expressions. Minus 2 plus 4 is positive 2. So you get 2 over 2. And minus 2 minus 4 would be minus 6 over 2. So it looks like as solutions that we get 1 and minus 3. And if you're curious, if you want to test to make sure these are correct, you would plug it into that starting equation, x squared plus 2x minus 3, and see that it does in fact equal 0. So you can test it. If we put in 1 anywhere we see an x, we get 1 plus 2 times 1, which is 3, and then minus 3 gives us 0. So 1 works. If we put minus 3 in here, minus 3 squared is positive 9. Then you'd have plus 2 times minus 3, which would be minus 6. So 9 minus 6 minus 3, and that also simplifies to 0. So it looks like both of these solutions pass the test, so we can be confident that x is in fact 1 and negative 3 for this equation. And with that in mind, let's look at essentially a more complicated example. Let's say we have that y is equal to 3x squared plus 4x plus 7, where in this case our a value, that number multiplied by x squared, is 3. Our b value, the number multiplied by x, is 4. And our c value is this constant back here. It looks like positive 7. And now we essentially just have to plug everything in to this quadratic formula. And again, I'll just rewrite it so that we have it. So we can say that x is equal to the opposite of b, so that'd be minus 4, plus or minus, we've got b squared, so that's 4 squared, which is 16, minus 4 times a, which is 3, times c, which is 7. And then all of this is divided by 2 times a, but a is 3, so 2 times a is 6. And now we just want to simplify this. We get minus 4 plus or minus. We've got 16 minus 4 times 3 is 12. And 12 times 7 would be 70 plus 14, which is 84. So we get 16 minus 84 underneath the square root, all divided by 6. And the 16 minus 84, this is going to evaluate to something negative. So let's pull this over here. 16 minus 84. And if you ever want to do this in your head, you can essentially switch this, make it 84 minus 16, and then just put a negative in front. So it looks like minus 68. And if you have the square root of a negative number, we're now dealing with imaginary numbers. And so what you can do is essentially we want to get this negative out of the square root. And if you ever have a product under your square root, namely minus 1 times 68 in this case, you can separate that into a product of square roots. So square root of minus 1 times the square root of 68. And we know that the square root of minus 1, we've defined that as I. That is the imaginary unit. So we can rewrite this as just I times the square root of 68. And if you prefer, we can even try and simplify 68. But if we make a tree with this, we have 68 would be, let's say, 2 times 34. And then 34 we can break up into 2 times 17. We do, in fact, have a perfect square in here. So 68 is the same thing as 2 squared times 17. So we could simplify this square root of 68, as the square root of 4 times 17, and then we can actually take a square root of 4. Remember, we can break up this product into a product of square roots, and so this just becomes 2 root 17. And so the end result here, this I root 68, this becomes I times 2 times the square root of 17. So we can replace that essentially right here. So let me continue on. I will carry this to the right here. So we get minus 4 plus or minus 2I root 17 all divided by 6. And one further simplification we can make to this is notice that the two terms in the numerator are each divisible by 2, and the denominator is divisible by 2. So we're going to divide every term by 2. So we get minus 2 plus or minus I root 17 over 3. So we've essentially just eliminated a factor of 2. And from here, we essentially have our two solutions. So I'm going to break it into its positive and its negative cases, just so you can more explicitly see that there are two answers here. So we have minus 2 plus I root 17 divided by 3. And we also have minus 2 minus I root 17 over 3. And you might be wondering, what graphical significance is an imaginary number as the solution? Or I should say a complex number as the solution. Because remember, when we were looking at these parabolas, we're looking at where it crossed the x-axis. But since we didn't get real numbers for this, that essentially tells us that it never crosses this x-axis. Because unless you're getting a number like 5 or 7 halves or 3.27 something, these are all real numbers, but you're not getting any of those. If we ever get something with I involved, that essentially tells us that it never crosses this x-axis. So in all likelihood, we're dealing with some kind of parabola that might look something like this, where its vertex, the lowest point of this parabola, is actually above this x-axis. So it's never actually crossing. So basically, in summary, if you ever get imaginary numbers as the solution using the quadratic formula, that just tells you that your parabola never actually crossed the x-axis. So there are no x-intercepts for this equation. And with all of this in mind, let's look at one further example.